often in computer science.
So why is it called a latch? Well, it's called a latch because once you try and change it, it latches onto the new memory. So it's latching down. Okay. Can anyone take a guess why this might be problematic?
Once it's down, does it go up?
Once it's down, it can go back up once you tell it to control. So it's latching onto the value quickly after it changes its value. Why may we not want the value to quickly change? So it might be a little hard to see. Think about the propagation delay of your circuits. Are all circuits going to consume the same amount of time to complete? No. So what does that imply about a latch? Because a latch is going to do it as soon as it can. May there be some times where you wouldn't want that.
You'd want it to wait until
all the other circuits were completed. Does anyone know how we do that? We use it. What tool we use in order to do that? We talk about it all the time with processors.
Is it like you're talking about the program, like the pound and then the number of times going through?
So that's in Verilog.
Delay,
Clock. So what we do with our clock cycle, nice, is we say it takes this amount of time for all the circuits to saturate. So we want we really want the latch to hold its value for the whole time cycle so all the circuits can properly saturate before we go into the next value, right? So there's this clock cycle where we want to wait. And a latch isn't going to wait. It just does it as quickly as it can. So the next thing, which is a flip-flop, is going to wait based upon your clock for your circuit to complete. So latch, it's level sensitive trigger, no clock. The flip-flop is edge triggered with the clock. So notice with your clock, so you have a clock. Why are there two signals here? All right, state variables change at clock edge. Basically, the variables change when the clock rises or the clock goes down. Hopefully, you can tell that it takes some time for the electricity to drain. That's how quickly things happen. Clock high, state changes occur, or active low, they change on the bottom. In other words, your values, you either want them to change going up or coming down, which means that if you do it on the up, it changes here, nothing happens until it comes back up. And then that will be your clock cycle, or your clock period, is how long it takes to go from one rising edge to the other rising. And that's if you're using an active high clock signal. If you use active low clock, then you're doing it from low to low. You just have to choose which way you want to do it. Ta-da! All right, so all processors have a clock. 3.2 gigahertz means cycle time is 0.31 nanoseconds, so not too much time. If I recall correctly, light can travel about, I think it was 11 or 12 inches every nanosecond, something like that. Yeah.
Interesting facts.
The more you know.
The more you know. Well, I mean, if it only can go 11 inches, then that's how much circuitry you can etch in before you have to wait the next clock cycle, right?
This is true.
Yeah. Remember physics.
Facts. Yeah.
Light is pretty slow. Okay.
Okay.
Yeah, I just went there.
I'd like to see you move that back.
I didn't say Wow. All right.
Judging light.
Man. Okay.
Yeah, light's got its own problems, okay?
So how does a flip-flop work? You have, we call them the D latch is the master and the SR latch on the end is called the slave. Notice that the control line going to each one of them. What?
It's called a slave? It has feelings too. Did
I just talk about personifying circuits?
I don't even know what I'm supposed to say to that. All right, that's what we call it. I didn't come up with the names.
This is the South.
All right. So the idea, notice that the final output doesn't occur until what the SR latch is. So first off, the best way to think about this is that the flip-flop actually has two memories in it. And it has the one that's currently putting out, and then the next one that's coming in. That's what's coming on or happening at a high level. And the slave is what's spitting out the final issue, and the master is what's going to change the slave SR latch. Okay. So, the D flip-flop's control input either enables either the D latch or the SR latch. Notice it's only enabling one of them. This is kind of how the flip-flop is going to work. Notice here the C is the clock. So if the clock is high, you're only enabling this guy to change, but you're disabling changing to the D latch. While if the clock is low, you are enabling a change to the D latch, but the SR latch is going to hold its old value because that's what C is. So do we get better pictures? As soon as C becomes 1, the rising edge of the clock, the master is then disabled. So he's going to hold whatever value he has and spits it to the SR latch. Any subsequent changes to D latch, while C is 1, will have no effect, so D can change all at once. Then the SR latch becomes enabled and its state changed to reflect what the master's was coming in, because the notice here with the master Q and Q naught would go into S and R, which again is the D input value from right when C became 1. So do you see how this is where we get flip-flop, because it flips and then flops. You could have done the tick-tock. We could have come up with a different name. Tick-tock, tick-tock. We just called it flip-flop, flip-flop. That's all. All right, so that was positive edge. Yeah, positive edge triggered, because notice that what triggers it? When C becomes 1, that triggers the change out here. But you could how could we make a negative edge trigger? So notice when the C goes to 1, that's when you disable the D latch and then enable the SR latch, and that changes the final output. The question was, how could we make it negative trigger?
Not before the other.
Right, you just move the knot down here. Okay, let's go ahead and look at this, because I think this will clarify a lot of what's going on. Q and Q naught. Q is 0. We'll just say, for the sake of argument, remember the 2 at the bottom are the values coming out of your memory cell. So currently we're saying Q is 0. The clock is low. We're using a positive edge. We should be using positive. Yeah, we're using positive. We're having D. We're going to rise it up. So if you think about that, while the clock is low, that's going to enable the D latch. So the latch, the master latch, is going to then hold on to the value 1. Now, even though it's holding on to 1, the whole memory cell is putting out 0 because that's what was in it to begin with, in the SR latch. When the clock goes high, that means it's going to take that value of the D latch and lock it in, because it's going to disable this guy, so he's locked in as 1. Then you're going to enable the SR latch. Well, Q is 1, he's now enabled, so since he's enabled, there's going to be a little time delay from the master latch to go through the SR slave latch to then finally become the output coming out of the entire flip-flop. Okay? Since you're up here high, the clock is still high, it actually doesn't matter what happens to D. D goes to low, so it's here D, what is it? D goes low, but he's currently disabled because this is high, so we don't care. He stays 0. This is supposed to signal the fact that the D latch is changing, but that doesn't matter. Again, D is back to 0 here, and now we're finally going to raise the clock again. So since D is here, the D latch is 0, moves over to SR latch on the rising clock, which then gives you a little delay for Q and Q naught to finally change. Okay. Let's see. Rising, D goes high, clock goes down, doesn't care. Notice that D went back to 0, which means that the D latch is going to hold 0, so when it rises again, it's going to change SR back to 0, but it was already 0, so it's going to just stay 0. Okay? Everyone see what's going on here? So the changing of a flip-flop is based upon a clock, and which is very useful because that means the flip-flop is going to hold its value for the entire clock cycle, and then it will change on the rising or negative edge or lowering edge, depending on how you write it. Okay, any questions? Okay. Here's some more timing numbers. We actually don't care about that too much right now. All right, sure, we'll look at the, what is this? One last thing to worry about. What is the starting value of Q naught? This is very common, is that in your processor design, you'll have a mask for your clock to make sure all the clock goes to your different parts at the same time. On top of that or underneath that, there's a special circuit called reset, which does send a signal to every part of the processor, namely your memories, to go and reset them. So it's just a way to override it, to have SNR come in to go ahead and reset them. This is special. You hit the reset button. That's what it's doing. It's literally clearing everything inside your processor, all the memories, sets it back to 0 because it's calling reset, and then when it comes off, basically these two guys are ignored. Okay. Negative. Notice that the inversion was over here now. That's all. Good. Any questions? Latches and flip-flops? Not yet. Great.